just one sloppy solder connection can cause all this equipment to completely fail. That's why it's so important to learn how to solder properly. Soldering is a skill that requires both knowledge and practice. Soldering is the joining together of metal parts by applying solder and heat to them. When the solder is heated to a high enough temperature, it becomes a liquid, which flows onto and slightly penetrates the metal surfaces of the connection. As it solidifies, the solder bonds the metal surfaces, producing a good electrical and strong mechanical connection. The basic purpose of soldering is to make a good electrical connection that's also mechanically strong. Each time you make a good connection, the solder is heated to its melting temperature and flows over the leads to be interconnected. The solder actually penetrates into the pores of the metal to be soldered. This embedding of the solder into the surface of the metal leads is called wetting. Good wetting is indicated by the solder feathering out to a thin edge. This is an example of good wetting. It's the wetting process that actually provides the physical strength and makes the good electrical connection. Here's another example of good wetting. The ability to wet the leads with solder is the secret of good soldering. The solder used in electronics is a mixture of tin and lead. Both tin and lead melt at temperatures much lower than most other metals. So the applied heat melts the solder but not the leads. That's why solder can be used to join metal leads and wires so conveniently. The tin and lead can be mixed in different proportions to make solders with different characteristics. For example, this is 40-60 solder. It's a mixture of 40% tin and 60% lead. This is 60-40 solder, the most commonly used type of solder in electronics. It's a mixture of 60% tin and 40% lead. Because 60-40 solder quickly changes from a liquid to a solid, there's less chance for lead movement to occur while the solder is soft, causing a poor connection. A low melting temperature and a narrow soft range are two reasons why 60-40 solder is the most commonly used grade of solder for electronic work. To make a good solder connection, the wires and leads must be clean. This looks like a clean connection, but because it's exposed to the air, an invisible insulating oxide layer has formed on the metal surfaces. The solder will not flow and stick to the wires unless the oxide is removed. Removing the invisible oxide layer is the job of a chemical substance called flux. Most solder used in electronics is actually a type of miniature tubing that contains the flux built into it. The flux automatically removes any oxide from the metal to be soldered as you apply the solder to the heated connection. The two most common types of flux are rosin and acid. Acid core solder should never be used for soldering electronic connections because it is highly corrosive. Acid core solder is used primarily in sheet metal work. Only rosin core solder should be used in electronic soldering. Rosin core solder is available in several diameters. The larger diameters are used for most general electronic work, such as terminals and connectors. The smaller diameters permit better control of the amount of solder being fed to small connections, such as those on printed circuit boards. To make a good connection, you've got to heat it to a temperature somewhat above the melting point of solder. That's the job of the soldering iron. Soldering irons come in many sizes and shapes. They're rated in terms of wattage, an electrical characteristic that tells how much power they consume. The bigger the connection, the more heat it drains from the iron, so the higher wattage iron you'd need. For most electronic work, you should use a pencil iron with a wattage rating in the 25 to 60 watt range. For your own personal safety, you should use a soldering iron with a 3-wire AC power cord. This wire grounds the iron's exposed metal frame and tip to prevent electrical shock hazard to the user. In addition to safety reasons, a grounded tip helps protect voltage and current sensitive components, such as delicate MOS ICs and MOSFETs. These devices are very sensitive to leakage electricity and static charges. A pulse discharge from a soldering iron can ruin sensitive MOS devices. So always use an iron with a grounded tip. Never solder in circuits that are on. If the iron's grounded tip touches a live circuit, you'll cause a short circuit and possibly damage the equipment. Some irons allow you to change to different temperature tips. This iron features 600, 700, and 800 degree Fahrenheit tips. Select a tip temperature based upon the size of the solder connection and the temperature sensitivity of the components. A 700 degree tip temperature is good for soldering or unsoldering most electronic connections. A 600 degree tip is good for PC boards with thin or delicate foil, while an 800 degree tip is good for connections with more area to heat, such as multi-layer printed circuit boards. Don't confuse heat with temperature. Heat is what brings the connection and solder to its melting temperature. It's important to transfer heat from the iron's tip to the connection as fast as possible so as not to damage the PC board or components. That's why soldering iron tips come in many sizes and shapes. This allows you to select the tip that transmits the most heat and allows greatest accessibility to the surface you plan to solder. As you begin heating a connection, your main concern is to place as much heated soldering tip surface in contact with the connection as you can. Two shapes that allow you to do this in most cases are a pointed tip, such as the conical or pyramid, and a flat-sided tip, such as the screwdriver or chisel. The screwdriver or chisel tip works well when you solder wires to flat terminals. The conical or pyramid tips are good for soldering thin wires and component leads to holes in PC boards. As you use your soldering iron, its tip will become dirty because of a buildup of oxides and dirt. All this contamination reduces the amount of heat that can be transferred from the iron to the connection. That's why you should get into the habit of cleaning your iron's tip practically every time you pick it up. You can do this by quickly wiping the tip across a damp sponge just before you use it. Most tips are copper, plated with iron or nickel. Never clean plated tips by filing them, or you'll greatly reduce the tip's life. Instead, get into the habit of wiping the tip before you solder. After your tip is clean, you should tin it. Tinning means coating the previously cleaned tip with a layer of fresh rosin core solder. A good coat of solder will protect the tip from oxidation and increases the amount of heat transferred to the connection. There should always be a layer of bright solder on your iron's tip. That's why you should get into the habit of regularly cleaning and tinning your iron. Once tinning is complete, you're ready to solder. In summary, we've seen that soldering is the joining together of metal parts by applying solder and heat to them. The basic purpose of soldering in electronics is to provide a good electrical connection that is also mechanically strong. In any properly made connection, the solder actually penetrates into the pores of the metal being soldered. This embedding of the solder into the surface of the metal is called wetting. Good wetting is indicated by the solder feathering out to a thin edge and is the key to making a good solder connection. Don't confuse wetting with tinning. Wetting means the solder is penetrating into the pores of the metal to be soldered. Tinning means a coating or layer of solder on the metal. For example, we can tin a wire or tin the iron's tip. You should clean and tin your iron's tip regularly in order to make good solder connections. It's important to remember that the purpose of a soldering iron is not to melt the solder itself, but rather to heat the work or parts to be soldered to a high enough temperature to melt the solder when the solder contacts the work. In part 2 of this program, we'll cover how to solder and unsolder. Remember, the basic purpose of soldering is to make a good electrical connection that's also mechanically strong. A mechanically strong connection means that instead of just passing a wire or lead through a terminal hole, you should wrap the wire around the terminal. By mechanically securing the lead, you'll get a more solid physical support, and it'll also keep the lead from moving while the solder is cooling. On printed circuit boards, components are usually mounted flat against the board. Now you're ready to solder. The 4 basic steps to soldering are: wipe the tip clean, heat the connection, apply the solder to the opposite side of the connection, leave the tip on only long enough to thoroughly melt the solder. Let's try this. First, clean the iron's tip by wiping it on a damp sponge. Tin the tip if necessary. The tip must have a good coat of solder to quickly transfer heat from the iron to the connection. Then heat the connection by placing as much tip surface as possible against both the lead and foil. Apply the solder. A small amount of solder applied to the tip will help the transfer of heat. Then the solder should be moved quickly to the opposite side of the connection. Remove the solder first, then the iron. Let the connection cool undisturbed. Then cut off the excess leads. It's good practice to remove the flux residue after soldering because it doesn't look good and it tends to collect dust and other foreign matter which could cause electrical leakage paths. After the solder has solidified, the flux residue should be dissolved with an approved solvent. Applied with a bristle brush or sprayed, and the dissolved residues removed with industrial wiping tissues or other absorbent material. A clean part of the tissue should be used each time to avoid the possibility of transferring the dissolved flux back to the connection. Then check your work. Remember the key words, smooth and shiny. A good connection is smooth and shiny. The solder should feather out to a thin edge. This is a good connection. Now let's look at some poor connections. This is a cold solder joint. It has a dull, gray, grainy, or crumbly appearance with poor bonding quality. Cold solder joints are usually caused by lead movement while the connection was cooling or by insufficient heat. This is a good connection. This is an excessive solder joint. It has more solder than is necessary to make a good connection. The heavy solder buildup obscures the wire or lead outline. Excessive solder joints are usually caused by applying too much solder or using too large a diameter solder. An insufficiently soldered joint does not have enough solder to provide a good bond between the wire and the terminal. It can occur if not enough solder is used to cover the connection or using too small a diameter solder. Burned or melted insulation is unacceptable and should be removed. The insulation must be close to the solder connection, but must not be included in the joint. Be careful not to make a solder bridge when working on connectors with closely spaced terminals. Or on PC boards. Solder bridges occur when adjacent terminals or traces are accidentally soldered or shorted together due to using too much solder. Using too much heat is the #1 cause of PC board soldering faults. If you overheat the green-colored epoxy glass PC boards, you'll cause white spots called measling. In addition to not looking good, measling can introduce paths for leakage and contamination. Measling is unacceptable if there is a continuous path between two conductors or pads. Too much heat can also cause a pad to lift. Make it a habit to apply the least heat possible to do the job properly. If you have to remove and replace a defective part, or if you solder a wire to a wrong terminal, you'll need to know how to unsolder. The tools you use to solder can also be used to unsolder. However, unsoldering can be done much more easily with tools especially designed for the job, such as a vacuum bulb, solder sucker, desoldering iron, or desoldering wick. The best way to unsolder a connection is to remove the solder from it and then disconnect the leads. Here we're using a solder sucker to remove the solder. To use it, you cock it by depressing the plunger. Then melt the solder on the connection, remove the iron's tip, and quickly insert the tip of the solder sucker into the molten solder. Release the plunger, and the solder will be drawn into the sucker. Allow the joint to cool, then repeat this procedure if necessary so that you remove as much solder as possible. Removing as much solder as possible will make it easier for you to free the leads without damage. The vacuum bulb and desoldering iron are used in a manner similar to the solder sucker, except that you release a squeeze bulb instead of a plunger. A key point to always keep in mind when working on PC boards is to avoid excessive heat. That's why you should never put the tip of a solder sucker or vacuum bulb on top of the iron. This extra pressure can cause the iron to burn the board. Desoldering wick or braid can also be used as an easy and effective way of unsoldering a component or touching up a printed circuit board. It's especially useful in unsoldering hard-to-reach connections where a vacuum device won't fit, or where the solder to be removed covers a large area, such as a solder bridge. Desoldering wick is a mesh of fine-stranded rosin-coated wire that absorbs solder like a sponge absorbs water. To use desoldering wick, place some of it on the connection to be unsoldered, then press a hot iron against the wick. The solder is drawn up into the wick as the iron melts the solder. Remove the wick and soldering iron simultaneously. After you're done, cut off and discard the part of the wick that is filled with solder. As with any desoldering technique, it should be repeated as necessary to make sure all the solder is removed. After you remove the solder from the connection, it should be fairly easy to remove the lead or wire with long-nosed pliers. Pry the lead loose gently, breaking away whatever thin layer of solder is left holding it. Be careful, as you can still cause damage. Removing ICs from printed circuit boards is probably the most difficult type of unsoldering. If you don't need to save the IC, you can cut each pin. The IC body is then removed, leaving all the pins still soldered in the board. The pins can then be removed one at a time by heating them with a soldering iron and pulling each one out with needle nose pliers. The clip-out method is also a good way to unsolder components with thick leads. Thick leads require more heat to unsolder, which could cause the PC board pad to lift. By first clipping out the component, you'll need less heat to unsolder the connection, so there's less chance of heat damage. Then each hole must be cleared of solder. You can use a vacuum bulb, solder sucker, or insert a toothpick in each hole to force out the old solder. If you need to save the IC, you can unsolder it by heating each lead, then remove the solder using a solder sucker or vacuum bulb. One way to do this is to rest the tip of the solder sucker against the pin next to the one you're unsoldering. When the solder is melted, just roll the tip of the solder sucker over it and release the plunger. Carefully remove all remaining solder from the PC board holes with a toothpick or solder sucker. In summary, we've seen that in order to make a good connection, the metal surfaces must be clean. Ensure a good job by getting off to a clean start. Mechanically secure the wire or lead by wrapping it around the terminal. Now you're ready to solder. To make a good solder connection, first wipe the tip clean and tin it if necessary. Then heat the connection. Place the tip against both the lead and the terminal. Keep it there until the total joint is hot enough to melt the solder. A small amount of solder quickly applied to the tip will help the transfer of heat. Then move the solder to the opposite side of the connection.